Hi, my name is Griffin Rice, and this is my report for Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to observe Faraday's law in action by conducting an experiment using a magnet and a tube of aluminum foil, and using this experiment to create a conceptual model based on the data gathered to further our understanding of how Faraday's law works. In this experiment, we can assume that there are no other forces acting on the magnet besides gravity and the magnetic force of the induced current in the foil. And just to preview the results, the average fall time from the experiment was 1.6 seconds, and the fall time in the computational model was 2.087 seconds. Some of the fundamental principles used in this lab are Newton's second law, used for the position and velocity update formulas of the magnet. Faraday's law, obviously like calculating the flux induced in the tube as a result of the magnet, the changing magnetic field of the magnet relative to the tube, and the Biot-Savart law, which basically just says that current creates a magnetic field. For the experiment, we dropped a bar magnet through a 46 centimeter long tube within a radius of 3 centimeters, and also wrapped in a 1 centimeter thick sheet of aluminum foil, and then measured the time it took for the magnet to fall through the tube. And then we repeated the experiment multiple times and got an average time of 1.6 seconds. Then here's a demonstration of the computational model. And then in the program, we define the initial measurements of the tube and the magnet, and also used the magnetic dipole moment and the function for creating the magnetic field from Lab 3. We also create a function for calculating the magnetic flux, creating the tube due to the changing external field from the magnet. Also include a calculation of the magnitude of the current in the rings that make up the tube, which is equal to the flux calculated by the function divided by the resistance of the ring. And then we also calculate the net force acting on the magnet, which is made up of two forces, the force of gravity as well as the magnetic force acting opposite to the gravity. And then also, lastly, the position and velocity update formulas for the magnet as it goes through the tube. Okay, and in the simulation, we had red and blue shaded areas moving down through the tube, representing the magnet and also indicating induced currents moving in different directions. In this case, the blue representing the counterclockwise, and red was moving in the clockwise direction. Basically, yeah, representing the increase in magnetic flux in the negative y direction, as well as the magnetic field in the positive y direction, opposing it, represented by the counterclockwise blue shade area. And if the magnet were flipped, the directions of the red and blue currents would also be flipped, so blue would be clockwise and red would be counterclockwise. Okay, and as previously stated, the results were 1.6 seconds as the average fall time in the experiment, and 2.087 seconds for the computational model time. Some potential source of error from the experiment, human error in timing the fall of the magnet, and also not dropping the magnet from the same height above the tube each time, could have been what led to the difference between the model and the experiment. To answer the first what if question, if the resistivity of the aluminum is reduced to almost zero, the magnitude of the magnetic field of the induced current would increase and therefore cause the magnet to fall even more slowly through the tube. And to answer the second what if question, if holes or slots were cut into the tube, it would have less complete rings of current, therefore decreasing the strength of the magnetic field and magnetic force. And because of this, the magnet would fall faster through the tube.